Let's get started. So what I want to do today is get started with second order differential equations. Start learning methods for solving second order differential equations. So that will be the goal today. So some of the common differential equations you've already come across. So I'll just start with that to motivate. Just as we started common partial differential equations. Okay, I'm going to write a few more on the board, and you can start thinking about what they are. At least the first three you may be able to recognize. All right, the first one. What is it? A simplest second order differential equation, simple harmonic oscillator. Okay, so this we have already come across. This also you have come across. What's that? Bessel. Okay. Bessel differential, that's what we did last time, right? So I've written a slightly different notation, but that's what it is. This is Bessel differential equation. And this one, maybe some of you have seen it in electromagnetic Simonov. Electrostatics. If not, you'll see it. I mean, you'll see it in 541. That's Legendre differential equation. Okay. So one of the thing is, in this case, this coefficient is this second coefficient is the coefficient of second derivative is exactly the derivative of the first one. So that has a very important property eventually. Okay. So that that's one of the things. Okay. Here, that's not the case in other cases. Okay, and these things, many of you perhaps who've taken quantum mechanics may have come across. This is Laguerre differential equation, which, some version of it will come, associated Laguerre will come in hydrogen atom problem, okay, when you solve. So it's called Laguerre differential equation. You'll see it in quantum mechanics. A version of it, which is associated Legendre differential equation, associated Laguerre differential equation, and this is a quantum mechanical oscillator. This is a classical oscillator. This is a quantum mechanical oscillator. Okay, so this is also something you've come across in quantum mechanics. So obviously, we need to know how to solve these differential equations. We cannot, except for the first one, we cannot guess the solution. We have to have systematic methods for solving such equation. Okay, so this again, you'll see these are two things will come across in quantum mechanics. This you will come across in definitely in electrostatics. You will come across. So we need to know how to obtain solutions of such differential equations. So that's a goal, today's goal, how to solve generally when the equations are somewhat complicated. So we'll first get started with some general definitions, which perhaps most of you know, but just to be getting started. An nth order differential equation, we can write it in this form. The most general differential equation I can write is nth order. So we need to know the definition of order. By order, what we mean is the highest differential that comes. Okay, so this is nth order because that's the highest derivative is nth order here. We have nth derivative of y with respect to x. So this will be nth order. And the right hand side is not zero, so it's an inhomogeneous differential equation. So this is nth order inhomogeneous differential equation. I'm using D for differential equation. If it's a homogeneous differential equation, right hand side will be 0. Okay, f of x equal to 0. Something in which f of x equal to 0. So we'll first start with homogeneous differential equation in our study. There's another terminology which is also used. We have to know it's the degree of the differential equation. Okay. This is the power to which the highest order derivative is raised. Okay, so so what is this equation, this nth order? What more word I can add here? We have nth order, which defines highest derivative of y with respect to x. Inhomogeneous defines my right hand side is not 0. What is the degree of this differential equation? 1. So nth order linear inhomogeneous. I can insert the word linear. Okay, it's not a non-linear differential equation. We are not studying non-linear differential equation. So that terminology refers to the fact that I don't have any, I'm not studying something like this, right? I mean, okay, I'm not studying an equation of that type. Okay, so that's another terminology you might come across. So I just want to introduce that. We'll be confining ourselves to linear second order differential equation at this point, right? So this is just to introduce terminologies. Okay, so okay, I just want you to focus on that word. See, in general, you may have some coefficients multiplying each of these derivatives, right? In the canonical form of the second order differential equation, what we'll do is we will divide whatever is the coefficient of the second derivative, we will divide it through. Okay, so if you wrote it generally, this is what it will look like, right? A to x, d square y, dx square, something. Okay, a1x, dy dx plus A0x y. This homogeneous second order, it will be something like that. But what we will do in the Kinnock, because that's how we analyze the properties of some coefficient and tell you whether C solution is possible or not. So in this case, whenever I say canonical form, I have the coefficient of the second derivative of y with respect to x is 1. Okay, so we have something like this, where p of x is really a1 over a2, okay, something of that nature. It's linear. Homogeneous is of this nature. Okay, first we notice it's a second order differential equation. So what? It will have two solutions. So we have to. So it will have two solutions, right? I mean, some combination of. So whatever method we devise, we have to find both solutions y1x and y2x. And also the solution that you find y1 and y2x, they should be linearly independent solutions, right? I mean, a constant time first solution is not y2x, although that's a solution, okay? So y1 and y2 are y1x and y2x are linearly independent. So what do we mean by that? So we need to understand the definition of what we mean by linearly independent. So that requires the following. I'm going to define this. Wronskian is nothing but determinant of, if y1 is the first solution and y2x is the second solution and y1 prime is the derivative of the first solution and y2 prime is the derivative of the second solution, this determinant should be not 0 if y1 and y2 are linearly independent. Wronskian is just the definition of this determinant, okay? That's sort of one way of defining linearly independent solution, okay? Supposing you have something like this, you propose some solution. You had y1 and y2, then you form some linear combination. Is that the linear combination, is that linearly independent or not? I mean, when can it be linearly independent?
We make the coefficients
0. That's the only time it can be linearly independent. If the coefficients C1 and C2 are not 0, then y1 can be written in terms of constant times so, okay? So if C1 is not equal to C2, not equal to 0, then, you know, we can always write y1x is minus C2 over C1 times y2x. If this is a constant time a solution is not linearly independent, okay? So such although y1 and y2 are linearly independent, if you formed a combination, under solution yx, the way I try to do it, that can be linearly independent only if, in such a case, only when C1 equal to C2 equal to 0. That's because 0 equal to 0, right? I mean, sort of in the way. But let's always remember this is what we will use. You have found two solutions and you want to check for this linear independent, construct the Wronskian and check if the Wronskian is not, that determinant is not equal to 0. What's the definition of the Wronskian? I mean, if this is the determinant, how do you write the Wronskian? What's W? If that is the Can I write this like this? Y1
It's y2.
y2 prime minus y2 y1 prime. Okay, so that is what the Wronskian is, and that should be not equal to 0. Okay, for y1 and y2 to be linearly independent solution of your given differential equation.
Professor,
Yeah.
does it matter which one you label y1 and y2?
No, we don't. Y1 is just one of the solution. No, it doesn't matter. Yeah, it doesn't matter. Again, you will get depending on the method. You know what? Yeah, it doesn't matter. Y1 and y2 are two solutions. Those solutions have to be like we'll show sin x cosine x is for the harmonic oscillator. If you get it, if I call that as cosine x and this is sine, it doesn't matter. It is just it does not matter. Or this label is just to say there are two solutions which are linearly independent, right? I mean, at this point, sin x is same. Yeah. Okay. So the reason for putting, whatever the differential equation be, because in Bessel differential equation, a2x was x squared and all that, we have to bring it in this form first, okay? And then analyze the property of p of x and q of x before we propose a series form of solution, whether it's possible or not, and which form of series solution we want to suggest. Okay, so any given differential equation, second, put it in that form, analyze the property of p of x and q of x, and that's why that is important. Okay, so all right, Fuchs proposed that this was developed by somebody called Fuchs. He said that we could propose a solution of this form, a series solution of this form, okay, this is some series solution. It's an infinite series, right? I mean, where the series is expanded about some point x naught. Okay, the series you're expanding about some point x naught within the domain. What he said was the following: there are ways we could have a series solution if if p of x, that is whatever we have, about the expansion point, if it is not 0, it doesn't blow up, q of x at x equal to x naught is not equal to 0. That is, p of x and q of x are analytic functions, that is, well-behaved function. It's not becoming infinity. Then x naught is called as ordinary point. If such a point, such a thing exists, So this is classification of the point about which you are making the expansion of the expansion. Most of the time you'll take the 0 or something, but I'm just so if whatever the differential equation is, given differential in Bessel or Legendre, if you bring it to this canonical second order differential equation form and just examine the coefficient p of x and q of x and see whether, you know, if it is not equal to 0. If it is equal to 0, if it goes to infinity, we still have a way to do it, and so that's what is a Fuchs condition is. So in this case, definitely you have a series solution, but even if at x equal to x naught, p of x diverges and q of x diverges, but it diverges in the following way, then we still can propose a series solution. That's what Fuchs was saying. Okay, so this is, so the function is analytic. Yeah, p of x is analytic. Means well behaved at x equal to x naught, automatically is well behaved. But even if it diverges, let us say becomes infinity, or even one of them diverges, we have to check. We have to check whether x minus x naught times p of x, when you evaluate for x equal to x0, if this is finite and x minus x naught square q of x as x tends to x naught is finite, we may still be able to propose at least both solutions or at least one solution as series solution. We still can propose at least one solution using the series method. Except in this case, the series is a more generalized. It's not a simple solution series, but it's a Frobenius series. It's an infinite series, but there's some modifications out there. Okay, we'll talk about that particular case too next time. Okay, right now we are going to be talking, today we'll talk about the case where x naught is analytic, okay, fully analytic. So in this case, it's called ordinary point. In this case, the expansion point about which we are doing is called regular, x naught in this case is called regular singular point. All right. So what if, can you think of a case where, okay, what does this say? This essentially says that the function p of x can have, it can blow up only like 1 over x minus x naught. So q of x can only blow up like 1 over x minus x naught square. It can't blow up like x minus x naught to a q. Okay, then you still have, then it is, you cannot do it. It is, how they depend as a function of x naught. That's all it says. Now, what if I had p of x is, let us say I have a function which is exponential of 1 over x, p of x, and my expansion point is x equal to x naught is 0. What happens then? P of x, supposing always, I cannot remove it at all, right? So in that case, this is what exponential of x I can always write as what, like this, right? 1 over 2 factorial 1 over x squared. It's an infinite series like that. So even if I multiply by x times x px, I can never get rid of the singularity at x equal to 0. So in this case, x equal to 0 is an essential singularity. So we put it in this form and examine the property of p of x and q of x around whatever point we are trying to expand. If it is x not equal to 0, is the function fully analytic? That is, I just look at it. It has no singularity. Let us say it is x. The other one is x squared. Q, no problem, right? I mean now, but it has a singularity. But I can remove the singularity by this procedure. I may still be able to propose one of the solutions as a series, and we'll have to devise other methods to calculate the second solution using Wronskian, because I know how to construct an independent solution because I know Wronskian can build that, right? But if I cannot remove the singularity at all by this procedure, then x equal to 0 in this case is an essential singularity. So you can have, in this case, is an essential singularity. If I had x minus x naught, it will be like this, okay? Suppose the expansion point was not 0, but all right. Okay, so basically what I'm trying to say is we have to first understand about which point we are going to make the series expansion and classify the nature of singularity classify the nature of singularity of the differential equation based on and there are basically only three types of singularities that we are trying to talk about. X naught could be no singularity, means ordinary point. Okay, it could be regular singular point, which means you can remove the singularity. It is singular, but you can function is singular. P of x and q of x are singular, or one of them is singular. Then it's called regular singular point or essential singularity. Then we cannot propose a series solution at all, because that series will not converge at all, right? Is this clear? All right. All right. Okay, I've just written some differential equation, and this is your Legendre differential equation. Okay, so given this differential equation, what is P of x and what is Q of x first? P of, we have to divide through this, right? Yeah, so P of x is not minus 2x because we have to make the coefficient 1, okay? So that's how we decide what type of solution we have to propose. Q of x is L times L plus 1 divided by 1 minus x squared. Okay, so that's the first step. Okay, because my equation of P of x is this. P of x is the coefficient of y prime. Q of x is the coefficient of y. All right, if that is the case, how does this function behave, P of x? What are the singularities of the function P of x? And let us classify, you know, all these points. What is this point? What is this point? What is this point?
Ordinary and regular. Ordinary and regular.
Yeah, so x equal to 0 is, px is 0, so it's well defined, it's not infinity, okay? So p of x at x equal to 0 is 0, fine, and q of x at x equal to 0 is L times L plus 1. So both are finite. So this one is an ordinary point. What happens to x equal to 1?
Regular.
So p of x becomes minus 2x, 1 plus x, 1 minus x, right? So x equal to 1, it blows up, but I can remove the singularity. Okay, so p of x at x equal to 1 is infinity, but x times, but 1 minus x, x equal to 1, right? I said 1 minus x minus 1, x minus x not be, right? So x minus 1 times p of x at x equal to 1, what is that? Is nothing but, I can write it as negative 1 minus x minus 1, negative 2x, okay, 1 plus x, 1 minus x, evaluated at x equal to 1. This, I can cancel that. So that is nothing but 2 of 2x over 1 plus x at x equal to 1 is 2 over 2, which is equal to 1, okay, which is not equal to 0, infinity. Okay, so that's finite. So you cannot just stop at p of x. You should, both of them should satisfy that property. Okay, in some differential equation, one might be finite, but qx could be blowing up. So check. Don't just stop at one of them. Check for p of x as well as property of q of x. For that, of course, you have to do this: x minus 1 whole square times q of x. In this case, right? Q of x for this is this. What is that? I mean, it should not blow up. Okay. So for x equal to 0, what is happening? Is it x equal to 1? X equal to 1, sorry. X equal to 1, it is 0. Yeah. So that is 0, so that's fine. So q of x times x minus x0 square at x naught equal to 1 is 0. Okay, so this is something you have to first check before seeing whether I can propose a series solution. That will be the first step. So given a differential equation, transform into the canonical form and examine the properties of q of x. If it is good, either it's an ordinary point or it's a regular removable, x naught is a removable singular point, I can use this method. Okay, otherwise we cannot use this method. Okay, so that is the first check that has to be done. Don't just start using the series method. Okay. We'll go in more in depth next class, but I just. All right. So let's solve a problem for which we know the solution, right? And make sure this whatever we are trying to propose is really working, right? So what is P of x in this problem? What is Q of x for this problem? P of x is 0, Q of x, 1. All right? So, yeah, so P of x at x equal to 0, if I want to expand around that point, is fine. You know, they are well defined. P of x and Qx are analytic. Are analytic at x equal to 0. Therefore, we can make series, we can propose series solution at x not equal to 0. Therefore, we can propose series solution about x not equal to 0. So I'm going to start, so we are going to, this is the first step, right? We are going to propose the solution y is equal to a sub n, x to the power of n going from 0 to infinity. I have removed x naught because x naught is 0. Okay, expansion form, I've chosen this as 0. Okay, so I'm doing the expansion. So these are good for any point, but I'm just saying, okay, we can just do it here. So because we want a series to look clean and nice, the expansion about x equal to 0, if you can do it, just do it. All right, so that is my y. So the way the procedure is, so series, this is your series, and I will just take the first derivative and second derivative, right? And then in n x to the power of n minus 1, and going from 0 to infinity, y double prime is a sub n and n minus 1, x to the power of n minus 2, and going from 0 to infinity. All right? So I want to plug that inside that differential equation now. So y double prime, when you substitute for that, is nothing but a sub n, n minus 1, x to the power of n minus 2, n going from 0 to infinity, plus, I don't have first derivative time in this case, n going from 0 to infinity equal to 0. All I've done is just substituted all that, and I have to somehow come up with what is the coefficient a sub n. I mean, I have to guess that, right? I mean, okay. So what is happening to the series at n equal to 0? The first series? n equal to 1, 0. So it really effectively is starting from n equal to 2 to infinity, right? Alright, if I want this series to start at n equal to 0, what will I do? Should I try n minus 2 equal to the variable n prime? Okay. So then n is equal to n prime plus 2, so I can transform this to summation n prime going from 0 to infinity. Because when n equal to 2, n prime is 0, an is nothing but an prime plus 2, n is n prime plus 2, and this is n prime plus 1, x to the power n minus 2, which is n prime plus n going from 0 to infinity, a sub n x to the power n equal to 0. Alright? Now, of course, n prime is a dummy variable, right? When the summation infinite series, if you call it n prime, doesn't matter. I can call that m, x to the power m, or n prime as m, whatever it is, doesn't matter. So n prime is now a dummy variable. So I can write this equation as is a prime of, let's say a of n plus 2, n plus 2, n plus 1, x to the power n, summation n, plus a to the power n, x to the power n, summation n equal to 0. So this is the original differential equation. We use the series method, and then we are ending up with something of this nature. Okay, so our goal is to somehow get the some idea of how to calculate the coefficient. So what we have to do is the following. This is it's an algebraic equation, for n equal to, it has to satisfy this equation for n equal to 0, n equal to 1, n equal to 2. It has to be satisfied. So if I look at the coefficient x to the power n, one of the terms here, then I should have this satisfied. For coefficient x to the power n, that condition has to be satisfied. So that implies I have the following: an plus 2 is nothing but negative an over n plus 1 times n plus 2, or an plus 2 over an is nothing but negative of n plus 1 times n plus 2. Okay. So this is called as a recursion relationship. It tells me how the odd, even or odd coefficients are related, right? At least something it tells me. I mean, a2 over a4, I know how it should behave, or a2 over a2 over a0, how it should behave. I at least have some idea. So using that, I'm going to predict the solution y, right? I mean, that's what I'm going to do. All right, so I have got, this is a solution that we propose, series solution. And I have to somehow, I have this recursion relationship, and from there, how do I guess this coefficient? And that is the goal at this point. Okay. So supposing I write this, that's an infinite series, right? can I write that as what? What is it? It is really A0, x0 is 1, right? It's like this, right? I mean A1x, A2, x squared, and so on and so forth. Okay, it's an infinite series like that. We expand it. Now, I see the pattern here, right? I mean, supposing I choose, I mean, I choose A0 is 1 or not equal to 0, and I say A1 equal to 0. That is one choice. I can start the series, okay? So this is a possibility. The other choice is I choose A0 equal to 0 and A1 equal to 1. Because a constant time solution is always a solution. Doesn't matter, you know, I'm just saying this is non-zero and that is 0. Okay, that's what it is. So if that is the case, let's see what happens. So case 1, let's call this case 1. All right, so in the first case, if I chose that, I have, this is what I can come up with. I have A0, A1 is 0 because of this relationship. If A1 is equal to 0, then A3, A5, all the odd coefficients become 0. Okay. So what I have is y1 x is equal to this, A2 x squared, A4 x power 4, and so on and so forth. Okay, so that's the, so if I go with the first choice of A0 equal to 1 and A1 equal to 0, this is what I end up with. Okay, fine. Then I just take A0 out. Then, because I only can get ratios, right? I mean, that relationship. If I can somehow get these coefficients, ratios of these coefficients, and see what this infinite series becomes, then I may be able to guess the first solution. Okay. And of course, I can take A not equal to 1. That's what we'll do, but I kept it right now until I get the stuff, right? All I'm just saying, if you put A1 identical to 0, and this not equal to 0, then I will have all the odd terms disappearing. Now, what is A2 over A0? So we use a recursion relationship to get that. A2 over A0 is, I'm just putting n equal to 0, right? To get that is minus n equal to 0. So it is 2, okay, which I can write as negative 1 over 2 factorial if I wanted. I need to get the next coefficient is A4 over A2, but recursion relationship gives me only A4 or A2, right? I put n equal to 2, I will get this relationship, which is negative n equal to 2 is 3, 4. But my goal is to get this guy, A4 over A0. So A4 over A0 is nothing but A4 over A2 times A2 over A0. And I have all that, right? So that is nothing but 1 over 1, 2, 3, 4. So it's 4 factorial, right? So it was negative, I have a negative sign here, a negative sign, so that will cancel. So you can sort of see the pattern here now. The first solution is nothing but A0, 1. A2 or A0 is minus x squared over 2 factorial. And this is nothing but x to the power 4 over 4 factorial. I don't have to calculate this next one, I know. It'll become like this, x to the power 6 over 6 factorial. Okay, it's an alternating series. and it is even in x. Right? So that's an infinite series, and we, if you can guess this, form of in a closed form, that would be great. And in some cases you may not be able to do, but it's a series solution after all, so you can leave it in a series form too, right? Minus 1 to power. Yes, you have to tell me what I should write. X to power 2n. What should I put here? N factorial? And there, minus 1 to power n. Will that work, or what should I have? N equal to 0, we need 1, right? N equal to 1, yeah. So it is 2n factorial here, right? N equal to 1, so I need this, yeah. But what is this series? What is this series? Do you recognize this series as a function?
It's a sine.
What did you say?
Sine.
What is sine at x equal to 0?
Cos.
Cosine of x.
Cosine.
Cosine of x, it's an even function. Cosine is an even function. At x equal to 0, it is 1. And so this is cosine has to be even, sine is an odd function. So this is cosine of x, okay? So any function, can be written in a series form. So you have the key is to identify a series back to a function if you can, okay? So that's nothing but cosine of x. So some of the simple function, like exponential of x, you should be able to do. Sine of x, you should be able to do. Natural log of 1 minus
A naught.
Huh? A naught is that, but A naught I'm going to take it as 1. Okay, so yeah. So I'm good. So anything constant time a solution is a solution, right? It's not changing something so I'm going to be taking A naught as 1, okay? That's what I'm going to be doing. So in this form I did not originally put, but I'm going to substitute A naught equal 1, but you can take A naught, it doesn't matter, but 2 times cosine of x is the function form, doesn't change. So this is what we guessed previously, right? We had d square y over dx square equal plus y square equal to 0. We didn't have to know the methodology, right? We just say, okay, I'm going to try. What is it? What is the function which will give me back the right hand side to left hand side? And we just guess the simple harmonic oscillator solution. But this also tells me, although I used to use a completely different method. I said, oh, okay. I have got a differential equation like this, and if it then it must have a series solution, and I get the same result, right? Which is sort of completely coming from different methods. We are matching the solutions, right? So that is one solution. And what is the other solution? Case 2, if you repeat that, we'll get case 2 is the one where, what did we say? We're going to put this as 0 and that as 1. Okay, so that will give me an odd solution. So they're completely independent because of it. Cosine and sine x are a linearly independent solution because of the nature, because we'll have x cubed term and x to power 5 term and all that. So case 2, let's do it. So that way that's how you get both solution. So right, A naught equal to 0 and A1 equal to 1. And what happens is then so y2x is then, let's first write down fully and then we put this, okay. X equal to 0 is A0 plus A1x plus A2x squared plus a3 x cubed. That's the full expansion of that equation. And I'm going to put a naught equal to 0. Yeah, let us see. Yeah, so I just have it here. So a naught is 0, then a2 is 0. Don't just look it like that, okay? So automatically it will be 0. So if a naught equal to 0, it will say, it means a2, a4, all these even coefficients are equal to 0. Okay, all of them are 0. So I can write this, so all of them will be 0. So I have, the leading term is a1x here, a3x cubed, a5 x power 5, and so on and so forth. That's an infinite series. I'm going to now pull out a1 in this case, because the coefficients that I can get are, from the recursion relations, are ratios of these terms, right? Alright, so we go back here. So I need a3. What I need is a3 over a1. So I'm going to put n equal to 1. So I get n equal to 1 is 2 times 3. Okay, so this is negative 1 over 3 factorial. And n equal to 3, I will have a5 over a3, right? Yeah, next coefficient is that. a5, n equal to 3 is this. 3 plus 1 is 4. 3 plus 1 is 2, 5. And what I need is a5 over a1. So a5 over a1 is nothing but a5 over a3 times a3 over a1. So we have all those things, which is nothing but plus 1 over 5 factorial. All right. So we have this as minus x cubed over 3 factorial, and this one as plus x5 over 5 factorial. Next term will be negative. All right, so that is my second solution, y2x. All right, so how will I write that? That series. The series form, the solution for 1 to write. Can I write it like this?
2n plus.
So n equal to 0, I will have x, right? N equal to 1, that is negative, this is x cubed, and that is 3 factorial, and n equal to 2 will become positive. So it's an alternating series, so I need to have this. Okay, so that's your second solution. Okay, so you could leave your solution like this if you could not recognize the series. But it's always, I'm going to tell you, always try to recognize with the function because of the method that I'm going to tell you, talk about the Wronskian method to guess the second solution. So then what is this? This is nothing but sine of x. Okay, so this is cosine of x. I'm going to put a1 equal to 1. So this is sine of x. So what's the Wronskian in this case? Just check whether they're linearly independent solutions. Wronskian is nothing but the determinant of y1, y2, y1 prime, y2 prime, right? So this is what cosine of x, it doesn't matter, we call that as, that doesn't matter. And then y1 prime is what? Cosine theta is 9. This is cosine x, right? Which is nothing but cosine square x plus sine square x is equal to 1, which is not equal to 0. Is this clear? Okay, so we are doing this because we are just checking the methodology works. I mean, this is a case, I know the solution, right? Because we can check it. So that way I have confidence I'm going to do other complicated differential equation. This methodology is going to produce the actual results, right? I mean, so that way we're building on that. Why are we doing such a complicated thing for a simple differential equation? Just to check. All right, let me now, okay, of course the most general solution is linear combination of that, okay? So the most general combination will be C sine x plus, what a D cosine x kind of thing. All right, okay, so what I want to do next is how to build a second solution from the Wronskian method. So you will see that when we do the other case when P of x and Q of x has a singularity at x equal to x naught, we may be able to get only one solution from the Frobenius series method. Okay, so we need to have the second solution by another method. Okay, so in those cases, the Wronskian method may come handy to get both the solutions. So as I said, Wronskian, now you know the definition is nothing but determinant of y1x, y2x, okay, that's the definition of Wronskian, and which is nothing but y1 y2 prime minus y2 x y1 prime. Okay, so that's the definition of Wronskian. Now, so W is that. Okay, so I'm just going to get rid of that so you can see it here. Now divide this equation by y1 squared. So we have W by y1 squared is nothing but y2 prime x divided by y1 x minus y2 x y1 prime x y1 square x. Alright, so all I've done is just divided. Now, can you sort of do something with the right hand side here? Does it, can I simplify that in some way? How can I write my right hand side? Can I write that as a whole differential of some quantity, and what is that quantity? I got y2 prime in the numerator in the first term, right? So can I write, I want you to guess what I should write as d over dx of something. At least one thing I can say is on the top, maybe I need that, right? Because I got y2 prime. What should I do in the denominator?
y1.
y1, right? So let's do y1 because that's the first term and the second term is negative 1 over y1 square of that, right? So we have that. So can I now integrate both sides? Integrate both sides with respect to x. So if I did that, what do I get? So can I say y2x over y1x is nothing but or what this is that the second solution, if you knew the first solution, you could get it through this expression if you knew how to calculate the Wronskian. But the Wronskian, the way, the definition I have, I need to know the second solution. So the expression that I gave you is not useful because that requires both y1 and y2, right? Y1, y2 prime minus y2, y1 prime. So I cannot, so the way, I have a formula, very general formula, but still I need to find another formula for Wronskian so I can make it useful, this one, okay? So I know that second solution can be guessed. I mean, we can, if I can calculate the integral knowing the first solution, but I don't know how to calculate this using that particular formula, okay? Because so I'm going to give an alternative way to construct Wronskian. I mean, that's one way. Another way is if you just know the differential equation, you can construct the Wronskian. Okay. So don't worry about this because I'm not put a lower limit because constant times a solution is a solution. It could be 0. It could be any constant. Okay. That's why I mean whenever you integrate this, you don't know up to a certain constant, right? I mean, because that's where it comes from. I mean, because when you differentiate that, a constant differential of a constant is 0. Okay, so that is arbitrary. In most cases, you're going to take it as 0. Okay, but it could be any constant, but any constant times solution will be a solution. Okay, I mean, so that's how they leave it. Okay, so the other formula for Wronskian is the following. This is one. But this is the most useful one for predicting the second solution. So I'm going to give you some constant exponential of minus bx prime dx prime dx. W is always a function of x. So where p is nothing but the coefficient in your differential equation in the canonical form, okay, which you always know. So if you knew it was a cosine x or whatever it was, you know how to calculate that integral. Okay, so we give another expression where the Wronskian can be calculated from a given differential equation. You don't need a solution to calculate the Wronskian. Okay, so this is a very useful formula. Okay, so let me tell you how we get it. So we go back to what we know, how we started, and then we. So all this we are trying to do for a general canonical differential equation, right? I mean, of this form. P is that with the first coefficient taken identically equal to 1. So when I say P, that is a P with the first coefficient equal to, or second derivative equal to 1. All right, so we have this formula, W y1 prime, y1, y2 prime minus y2. All right. So I'm going to take the first derivative of this with respect to x. W prime is first derivative, so I can write it as y1, y2 double prime plus y1 prime, y2 prime minus y2 prime, y1 prime, minus y2, y1 double prime. Okay, all I've done is just taken the derivative. I can cancel y1 prime. Yeah, I can cancel that. So I have first derivative of Wronskian is nothing but y1, y2 double prime minus y2, y1 double prime. Okay. Now, what is y1? y2 is the second solution, right? I mean, so y2 prime from that formula is nothing but, so y2 should satisfy this differential equation, right? y2 double prime px, y2 prime qx, y2 should be 0 because that's the solution of that differential equation. So is nothing but minus px of y2 prime minus qx of y2 minus y2 y1 double prime, which is minus px y1 prime minus qx of y1. Okay, so all I've done is substitute for these two from our differential equation because they satisfy, they are the solution, so I must have this true to be true, right? This must be true. Okay. All right, what do we see now? So what I have is first derivative of the Wronskian is this is minus qx y1 y2 and I have plus qx y1 y2. So these terms will cancel. So I'm left with minus negative px of y1 y2 prime minus y2 y1 prime. All right, and what is this?
It's just
Wronskian. Wronskian. So what I have is then dw over dx is nothing but minus px times the Wronskian. That's the definition of that when from there. Or I have dw over is minus px dx. So now integrate both sides with respect to one with respect to w, the other one with respect to x. Okay. So if you did that, integrate. Then this is natural log of omega, right? Natural log of omega is nothing but this. You can always add natural log of c also, right? Constant is constant, so you can, if you want, you could add c, natural log c, doesn't matter. But so I can write now w is nothing but constant times exponential of minus p of x prime dx prime x, if you want to add logs. So I never, up to a constant we can never, we don't know, so our solution. So Wronskian is nothing but, so that is the formula I have written. C will take it as 1, okay, but I'm just, this is how it's written. And that's a dummy variable and this is a function of x, right? So I have put the upper limit as x. You can take this as 0 or whatever you want, okay? So that is my formula for Wronskian, which is more useful for predicting the second solution because these are the three equations you have to know, right? I mean, to get the second solution in some sense. This is useful for checking whether they're linearly independent, and this is useful for getting the second solution. If you can, first solution times this Wronskian in the numerator, okay, y1 square x prime x, okay? So those are the, most important equation for calculating the second solution of a second order differential equation. So I want to go back and check for whatever we obtain for our harmonic oscillator, so we complete the whole thing, right? So just 5 minutes give me and we'll finish up. So we have done, this is my harmonic oscillator differential equation. So what is P of x here and Q of x here? Because I need P of x here, right? So what's P of x here? What do you say? What is P of x is the coefficient of y prime.
Okay.
So Q of x is 1.
Yeah.
So
Yeah,
P of,
sorry.
P of x is 0.
Yeah, sorry.
Yeah, so that's why you have to go back to your
Yeah.
original differential equation, okay? Canonical form is very, very important. Y double prime, P of x, y prime, Q of x, y equal to 0. So P of x is 0, okay? And let us say I'm trying to do y1 for me is, let us say, sine of x, okay? And I'm trying to get the second solution. So what's the Wronskian in this case? If P of x is 0, what is Wronskian? It's just constant, right?
Constant.
Yeah, constant 1 doesn't matter, okay, something, okay, because exponential is there. All right, so my second solution is then simply first solution, sine of x, right? Then I have to calculate this integral. Wronskian is in the top, which is a constant, okay? Divided by sine square of x prime dx prime, a constant, right? So a constant can be pulled out, so it is c sine of x. And what is integral of cosecant square x dx prime? I pull the c out. What is integral of cosecant square? What's the differential on the function, trigonometric function, which gives cosecant square? Cotangent x, right? Yeah. So that is so there is that, which is cosine of x. Okay, so this is nothing but c sine of x, cosine of x, sine of x. Okay, so y2x is nothing but this. C can be taken as constant, but 1. But anyway. So you're just closing the loop, right? So you can take c as 1, then it is cosine of x. All right. So this method is useful only if I can get my y1 in a functional form. If say you leave it in a series, it's not useful. So that's when this method is useful, because I have to do the integration, right? I need to have a functional form. If you leave it in an infinite series form, you will not be able to use this method. Okay, so that's why you have to understand a little bit, review how to go from series to function, function to series of some common functions, right? All the trigonometric function, natural log of 1 plus x, 1 minus x, those kind of a thing, and summation of t to the power of n, what does function form it becomes, all these things. Then it helps you to solve this problem, this kind of integration more easily. All right, let's stop here. Hope it was clear. We did a simple case today, a case where x naught is an ordinary point, right? The function p of x and q of x are well behaved at the expansion point of the series expansion. Okay, so that's the case we did, and next time I'll do a case when the function blows up at x equal to x naught, p of x or q of x, one of them blows up. So I cannot use a simple series method. I have to use something called generalized power series method. So so we'll get to the next stage of. So that way you know the techniques, all the different techniques for solving differential equations. That's cool. All right. Yeah. Let's stop here. So next time you have to give me the homework too. I mean, if you have any difficulty, please let me know. Okay. So.